for the kind introduction. Welcome, everybody. My name is Först from the Max Planck Institute for the Structure and Dynamics of Matter in Hamburg, Germany. I would like to thank the organizers for inviting me to this exciting conference. And also, I would like to mention that I'm very excited to be in this very nice place. Even more, I look forward to visiting the Basilica tonight. But before I do so, I still have the opportunity to give you this presentation, which I would really like to do now. So what I will try to tell you today is introduce to you the efforts of our group in using intense light fields in the mid-infrared spectral range that we tune into resonances with optical phonons in order to dynamically engineer crystal structures in a new way, in an unconventional way, in a nonlinear way, and with the goal of controlling functional, electronic, and magnetic properties. And the particular experiment that I will focus on today has been carried out on the antiferromagnetic cobalt difluoride, which at the same time is a piezomagnet. And I will show you how this particular type of optical phononic excitation can induce a net magnetization in this antiferromagnetic compound. So this work was carried out in the group of Andrea Cavalieri. So he's the head of our department for condensed matter physics at the Institute. All the hard work of this experiment that I will talk about has been done by Ankit Disa, a fantastic scientist who was with us as a postdoc for a couple of years, and now he moved back to the US, taking a position at Cornell University. Bia Long developed a dedicated source that I will use in the experiments here. And Michael Fechner, he's also a very lucky case for us because he's our in-house theoretician. So this is a very, very good person to have because you can talk to him every day as an experimentalist. And he's specialized in doing DFT calculations on phonons, on lattice dynamics, and how they interact with different degrees of freedom. The idea for the experiment that I will talk to you about today actually came up during a 2-week visit of Paolo Radaelli at our institute, where we discussed the possibility of carrying out this experiment, and Dharmalingam Prabhakaran, he grew the sample that we will investigate today. But before I go to the specifics of this experiment, let me please introduce to you the general goal of our research group. So we are interested not only in controlling magnetism, but also controlling the collective properties of other systems where the interactions of electrons determine the functional properties, right? And because these interactions involve multiple degrees of freedom, such as the charges, the spins, the orbitals, but also the lattice, and all these interactions, they take place on similar energy scales, these systems form very complex phase diagrams as exemplified, shown here for the case of a high-temperature superconductor, where you see that starting from an antiferromagnetic insulator at low doping, you start forming a superconducting dome. Another system that you might be more familiar with is this magnetoresistive manganite, where you see that by changing the concentration of some certain atoms, you can choose in which magnetic phase you will localize. What these systems have in common, though, is that they are extremely sensitive to external perturbations. For example, magnetic fields and structural control. And what you, of course, know is that if you apply a magnetic field to such a manganite, you will end up with colossal magnetoresistance, changing the resistivity over orders of magnitude. Applying pressure, for example, to such a high-temperature superconductor would change the critical temperature. So here, the structure is more important. And in general, I would like to highlight the importance of structure on the functional properties of certain systems in this comparison that has been put forth by Eva Pavarini a couple of years ago. So all these systems that I'm showing here, they all have one electron in the d shell. So this single electron should determine all the properties. But if you go here from left to the right, you observe that one is a metal and the other one is an insulator. And this is a result of the change in crystal structure. While here all the bonds are basically straight, from the left and to the right, you more and more distort the lattice. You have tilts and rotations, and then the bonds are no longer straight, and it's much more difficult for electrons to do electronic transport. So therefore, they go from a metallic to an insulating behavior. But at the same time, they also change their magnetic properties. While these two are paramagnets, this one is an antiferromagnet, and this one even becomes a ferromagnet. So structure is really important, and that's why we want to control the structure to change the functional properties of these materials. And while we are not interested in doing this via chemical composition, we try to do this by light. And as was already discussed by Alessandra's talk in the morning, if you use light, you have two advantages. One is you can do this probably or possibly very fast, much faster than you can do by any other means. But at the same time, you can often explore new states of matter that are far away from equilibrium, but that have very different properties than any equilibrium response of the material. But then if you do this optical excitation, you have to choose at which photon energy, at which frequency, at which wavelength you want to do this excitation. While, and here, phononic excitation in the mid-infrared, so where you tune your light field into resonance with optical phonons to coherently drive them, you have two advantages compared to the left and to the right. Or you have two big advantages. First of all, you avoid direct excitation of carriers, so you have far less heating, interactions, incoherent processes that lead to scattering with phonons, for example. So much, much more coherent process that you have here. And on the other hand, but you're already very close to the collective modes of macroscopic quantum orders, so you can very efficiently also couple to the ground states of these materials. And this is the big benefit of this phonon control. And indeed, the very first demonstration of such a vibrational-driven control of functionality was done in 2007 by Andrea Cavalieri when he was still in Berkeley. So tuning a mid-infrared excitation pulse into resonance with a certain phonon of a manganite induced an ultra-fast insulator metal transition, which was probed here via electrical transport. But we can do a lot more with this. First, I would like to highlight what we call light-induced superconductivity. So in these high-temperature superconductors, we have nowadays been able to achieve metastable, nanosecond-lived superconducting states far above the equilibrium critical temperature. Even at room temperature, we can achieve nanosecond lifetimes of a perfect superconductor. On the other hand, we are able to control ferroelectricity. So there's one example shown here. Strontium titanate is a quantum paraelectric, which in principle wants to become a ferroelectric material, but as you cool it down, quantum fluctuations prevent you from doing so, and we have shown that this particular type of phononic excitation can lead indeed to a metastable ferroelectric state also of this material. And lastly to mention, we can also control magnetism. First efforts have been done by our group, but also here I would like to highlight a result from a Dutch collaboration, also involving the chair of our session here, where iron garnet was being able to switch into a state where it shows a quadrupolar magnetic pattern like this here. And but today I will now focus on our work, how we can use this type of control, this approach for the control of an antiferromagnet. And to do so, I first have to explain to you in detail how light interacts actually with the crystal lattice. So assume you have a mode like this, which is, as you see here, infrared active. So as soon as this guy starts oscillating, you would induce a dipole along this direction. You can describe this as a harmonic oscillator, and the interaction with an electric field pulse can be very easily written down by this Hamiltonian, where Z star is the charge associated with this motion, and QIR is the amplitude of this atomic coordinate. You can write down the equation of motion now, and if you now tune your excitation pulse into resonance with the frequency of this phonon, you can see that as long as the pulse is present, you enhance the amplitude of this mode, and then it decays back to its original position. So this is a perfect coherent excitation of this vibrational mode. And while this is theory, we can also measure this. So this is a typical electric field that we are able to generate in our tabletop experiments. So this is a two-cycle field tuned to a frequency of about 17 terahertz. And here is, in particular situation, this is in resonance with a certain phonon mode in lithium niobate. And if you do a time-resolved measurement using second harmonic, that we have also seen before, that measures the breaking of inversion symmetry in this material, you can perfectly see what I just described before in this theoretical calculation. And you see a mono frequency response as shown here in the Fourier transformation of that curve. However, we are able to produce very intense light fields at these frequencies. We can easily reach megawatt per centimeter peak fields. And this will induce atomic displacements of order of 10 picometers maybe. This is up to 10% of the bond length that you find in these materials. And in this regime, you end up in a situation where nonlinear effects, where nonlinear interactions of the atomic motions become important. And also this we can measure as highlighted here. This is the same experiment as shown before, but just with a much, much stronger electric field. And what you see here is you not only observe harmonic oscillations, but particularly here, where the amplitude of this oscillation is supposed to be very large, you see that higher frequency components appear. And this is due to the fact that now you drive the system into a range of amplitudes where all the harmonic, the anharmonic terms of the potential have to be taken into account. And this then leads to high harmonics also in the motion of the atoms along this coordinate. So nonlinear phononics is real. But how can we use this to control functionality? So far, I've only shown you that atoms oscillate around equilibrium positions, and this probably will not change anything. So what you now should take into account is a second mode, which has a different symmetry. Now this is a Raman mode, okay? And what you learned at school, in linear fashion, of course, in linear order, they cannot interact with each other. However, already many, many years ago, decades ago, there has been proposed the following scenario, which was called ionic Raman scattering, which tells you that in the lowest order, there can be a coupling between an I-active mode and a Raman mode in that system, which is proportional to what we call Q squared Q, which is quadratic in the amplitude of the driven mode and linear in the amplitude of the coupled mode. And what this does here, shown here in a frozen phonon example, so if QIR is fixed but finite, you will shift the potential of this Raman mode from its equilibrium position to a new position. So this allows you to change the crystal structure along the coordinate of the coupled mode. And if you now consider this in the time domain, where we can drive this mode with an intense light field, so you see here the oscillations that I showed you before, this puts a directional force onto the Raman mode, and thereby it can induce a transient crystal structure for a short lifetime, but definitely this is no longer oscillating around zero, and therefore it allows you to change, to dynamically drive a distortion in the lattice where you can have different magnetic or electronic properties. And indeed, this is the idea of this scenario. So while this IR mode is ringing, you have a displacement of the lattice along the coordinate of the IR mode, and this enables the engineering of new functional properties. For example, in this way, you can easily transiently change bond lengths or bond angles, and in that way, you can control orbital overlap, you can change crystal field splittings, orbital polarizations, but on the other hand, also you can control anisotropy or exchange interactions. So there's a whole zoo of phenomena that you can induce now, and this allows us to induce all the changes that I've introduced to you before. But now let's come to the experiment that is probably most interesting for you, which is done on the antiferromagnetic cobalt fluoride. So as you may well know, this is crystallizing in a rutile structure, and the cobalt atoms, they arrange on a BCC lattice, and below the Néel temperature, which is 40 Kelvin in these systems, you find a perfectly balanced antiferromagnetic system. So we have two cobalt sublattices, two magnetic sublattices, one that results from the cobalts in the center and one from those on the corner of this cube. So this is perfectly balanced. But at the same time, this material is piezomagnetic, which means now if you apply strain along the in-plane direction, you see that you can induce a net magnetization that is proportional to the strain that is applied to the sample. And why is this so? What you know is, or what one knows is, so this is a D7 system, and the local magnetic moment, the orbital contribution to the local magnetic moment on each side is proportional to the inverse of the energy splitting of the T2G bands. And this is linear proportional to the distance d between the cobalt and the fluorine atoms that you have in this compound. And now when you apply strain, you make this bond here larger, and this bond you make shorter. So that means for the sublattice that is in the center, that regards the cobalt atoms in the center of this compound, they have a positive change in the magnetization while in the local magnetic moment, while those ones have a decrease of the local magnetic moment. So therefore, you unbalance the magnetic system, so that at the end of the day, you end up with a net magnetization. So this is a ferrimagnet, right? So you don't change polarization directions, you change the local magnetic moments. And interestingly, in contrast to magnetostriction, this is really linear to the strain that you apply. So if you apply a strain along one direction or the other, this will at the same time change the direction along which you induce this net magnetization. So, but the question is, can we do this with light, and maybe can we do it even better? So what you have to do is you have to change the distance between the cobalt and the fluoride atoms, right? When you do this with strain, at the same time, you change the size of the unit cell. Therefore, you cannot do this to infinite amounts because, at some point, the crystal will break because of the too much strain that you apply. However, and this was explored by Paolo Radielli when he was visiting us, there is a certain mode in the system, a certain optical phonon, a B2G symmetry Raman mode that breaks the symmetry of this compound, which actually has the same distortions, the same changes in bond length between cobalt and fluoride, and this in principle should lead to the same net magnetization induced in this material. And therefore, the idea was to find an excitation that can couple to this Raman mode. But as I said, it's a Raman mode, so therefore light cannot directly couple to it. We need to couple to it via an I-reactive mode. But at this time, because this is a mode that breaks inversion symmetry, or that breaks symmetry, this one, you cannot just or only pump one I-reactive mode, because in a Q-square fashion, this would only be able to couple to symmetric modes, but you have to excite two modes at the same time. So these are two degenerate modes. So one moving atoms along the A direction and one moving atoms along the B direction. But then the product here will lead to the excitation of this Raman mode and will displace it in the same fashion as I introduced before for this Q-square Q coupling in this general case. Okay, and so here's a simulation from Michael Fechner, my DFT colleague that I mentioned at the beginning. So as soon as you start oscillating here this way, you see that on average, this distance between cobalt and fluoride becomes smaller. This distance becomes also smaller. And then as soon as the atom stops ringing, also these go back to the original position. Okay? So can this indeed now lead to magnetization? So we did timeless or Faraday rotation measurements. And because this cobalt fluoride involves relatively light atoms, so the frequency of the optical mode that we have to drive is at 12 terahertz. So to this end, or to pump it, we had to develop a specific source that can produce very selectively narrowband pulses, which are, by the way, tunable between 5 or 4 and 20 terahertz. So now very easily we can tune this excitation across the whole terahertz frequency range. And using this particular type of mid-IR or terahertz source, we were then exciting the sample with a 45-degree angle between the A and the B axis. So therefore, and this is why this mid-IR pulse is slightly rotated away from the optical axis. And what we observe is indeed, in this Faraday rotation measurement, first a small blip at time 0, which we believe is a result of optical birefringence induced by the phonons itself. But then on the longer scale, you see a rotation of the polarization that's indicative of a change in the magnetization of the sample. So by the relating to the induction of a magnetic moment. If you do the same experiment with the zinc fluoride, which has exactly the same structure but is non-magnetic, you don't get this signal. So this makes us strongly believe that this is really a magnetic effect. And also we did optical circular birefringence measurement that also confirmed that a magnetic birefringence measurement that also confirmed that this is a purely magnetic signal. So ferromagnetism is observed. On the other hand now, because of this particular type of excitation where we couple to two phonons at the same time, by changing the polarization of the pump pulse, we can excite the two phonons with a different phase. And this would lead to the atoms, to the rectified atoms, moving either closer to the cobalt or further away from the cobalt, yeah? So in that sense, you should be able to reverse the magnetization that you induce in this material. And indeed, this is what we observe. So we repeat the measurements now for a 90-degree rotated pump polarization. And now the rotation, the Faraday rotation, goes in the other direction. So we can reverse the magnetization that we induce by this process. So we can study this effect as a function of the electric field that we apply to our sample, and indeed you observe a quadratic field dependence, which totally makes sense because each of the modes you drive linearly with the electric field. And on the other hand, if you now tune your excitation frequency over a broader terahertz frequency range, you see that the amplitude of our signal is resonantly enhanced if you're indeed in resonance with these degenerate optical phonons that we are believing to resonantly excite. Okay, so everything here makes sense at all. And lastly, one check you can do, you can investigate this effect as a function of temperature. So here are the time domain traces. At very low temperatures, you have a huge effect, but then the closer you go to the near temperature, this effect disappears, also shown here. And basically, it exactly follows the magnetic, the near temperature approach once you go down here in higher temperatures. Okay, so how can we now compare this approach of dynamical structure engineering with what people have done before, which is applying strain? First of all, the largest strain-induced magnetization achieved in this compound was of the order of 0.05 μ-Bohr per unit cell. In our experiments, we were going far, far higher here. So in principle, the maximum tensile strength that you could achieve in a sample that had ever been observed is of that range. So even there, you cannot go to the highest peak electric field, to the highest net magnetization that can be induced in this material. If you really wanted to achieve that number, you would have to apply 50 gigapascal of uniaxial strain, which is a lot more that you can really do. And what we also calculated, if we would be able experimentally to turn up further our excitation fields, we could maybe even go a factor of 2 higher here in magnetization induced in this material. So overall, I would like you to take home that nonlinear phononics exploits symmetry rules to induce specific atomic displacements in solids to engineer tailored functional properties. Yeah, there was a variety of phenomena introduced at the beginning, but also probably more interesting for you, you can induce magnetization, net magnetization in the compound that I showed you before. And of course, as you saw, it can circumvent limits of strain, particularly in terms of amplitude. And with this, I would like to conclude. So we believe that nonlinear phononics nowadays can be seen in the tradition of more established techniques that have been used so far to rationally design material properties by structural control, for example, strain, nanostructuring, also van der Waals heterostructures, or impurity atomic manipulation, or, for example, oxide interfaces where you change structure at the interface. And with this, I would like to conclude. Thank you for your attention.